Good evening, children. Once again, welcome all of you. So let me start sharing the screen without any further delay. Yeah. So I started sharing the screen. I hope it's visible to all of you. So we'll continue with electric fields and charges that we were looking at in the last class. Okay. So yeah. So electric fields and charges, we have seen some basic concepts. Basic formulas is what we have learned. It would be great, if you guys can recall. Let's have a quick recap because this is from 12th standard syllabus. So 11th we have seen major chapters, and now we are into 12th syllabus. So I hope you guys are practicing and you've learned few formulas positively. So if you can recall the formulas, it will be really grateful, because based on that we have many questions, and further also we are going to solve some questions based on that. Okay, so let's have a quick recap of all the formulas that we learned in the chapter electric fields and charges. So I'm just annotating now on the screen. I hope it's visible. Okay, so electric fields and charges. First and foremost, the concept that we learned was Coulomb's law. Okay, and a quantization of charge also we saw. We'll come to that. So who can tell me what's the formula for Coulomb's law? Please feel free to speak and communicate. Okay, so what is Coulomb's law, children? The formula for Coulomb's law? Anybody, if you can remember? It talks about the electrostatic force of attraction between two charges Q1 and Q2, which is separated by distance of r in space. Okay, so it is given by the relation F is equal to K times Q1 Q2 upon r square. This is Coulomb's law formula. Okay, where Q1 and Q2 are the charges in coulombs, and K is a constant. I told you it is a Coulomb's constant, and r is the distance of separation between those two charges. Okay, so the SI unit of force always remains as Newton. And what about the unit of charge? I hope you guys know the unit of charge is coulombs, and distance is anyways going to be in meters. Okay, so if these are the units of individual physical quantities, now who can tell me what is the SI unit of the Coulomb's constant K? So what can we do to find out the unit of K? We just go for a simple rearrangement. You keep K on one side, make the K as the constant, and then go for a rearrangement. So what do you get by doing so? You can write it as K equals F times R squared upon Q1 times Q2, right? This is how you can express. So what will be its unit now? It's very simple. It's an easier way to find out. Force, as I told, it's in newtons, and distance is going to be in meters, but here we have distance squared, so Newton meter squared upon Coulomb into Coulomb is going to be Coulomb squared, right? So that's the unit of K. Coulomb's constant has got the unit as Newton meter squared upon Coulomb squared. By rearranging, we can understand this. All right, and what's the value of K? When we solve numericals, we take the value of K as 9 times 10 power 9. Okay, that's the value. Along with the units, if you would write, it's again Newton meter squared upon Coulomb squared. That's it. All right. So this is all about Coulomb's law. We have had a quick recap about it. Now here, according to Coulomb's law, you can see that it builds a relationship between the electrostatic force of attraction between the charges and the distance itself between the charges. So what can you say? You can see that this Coulomb's force is inversely proportional to the square of the distance, right? So hence it is also called as inverse square law. So we also call it as inverse square law. So something to be noted. So what can you say that, what can you understand by the relation F is inversely proportional to R square? So if one of the quantity is increasing, it means that the other quantity is going to decrease drastically, isn't it? So what happens if the distance between the charges are going to increase? What can you comment about the force of attraction between them? if the distance decreases. If this distance decreases, the force of attraction is going to increase, and that's what inverse square law means. Okay, inverse relationship means that only. All right. So if one quantity increases, the other would decrease, and vice versa. So this is what we need to understand. If you want to draw a graph of force between distance, it's going to be an exponential graph. All right. So that's all about Coulomb's law. So with that, we'll move to the next concept that we learned. Let's have a recap about it. The next concept was quantization of charge. Okay, or you can say charge quantization. What was that? If you can recall, you can tell me. Charge quantization. What is meant by charge quantization or quantization of charge? So, electric charges can be transferred in small denominations or minimum denominations of integral multiples of electrons. So, that is what is meant by charge quantization. You can quantify charges in terms of minimum denominations such as integral multiples of electrons. So according to charge quantization, you can say Q equals N into E. That's relation, where N is an integer number and E is the charge of the electron. Okay, so that's the relation, children. That's what you need to understand by charge quantization. Okay, so with that, we'll move on to the next concept, recap. So the third concept that we learned was electric field. So we saw what was electric field. Okay. So electric field was given by the letter E. So capital E. So we said electric field is defined as the force acting per unit charge. Okay. The force acting per unit charge. You can write F upon Q, or it also can be expressed as F upon Q naught. Okay. So that's the formula for electric field. The amount of force that is going to act per unit charge at a particular point, then you say that there is electric field existing at that particular point. Okay. So electric field orientation, also let us see here. So when I take a positive charge, a small positive charge, now how is the electric field surrounding this positive charge going to look like? Okay. So around the positive charge, electric field will be radially outward. Now what do I mean by radially outward? It's going to move in all directions like this. Okay, just like the rays of the sun that come out. Okay, so this is what is meant by radially outward. So when you have a positive charge, the electric field lines around the positive charge, they always are directed radially outward. Okay, so when you map all the points, you will get a surface which is very similar to that of a sphere. So it's a spherical surface. And what will be its surface area? I hope you guys know the total surface area of a sphere is going to be 4 pi r squared. And if you know the distance r, you can calculate the total surface area also surrounding the positive charge. Okay. So for positive charge, the electric lines of forces or the electric field lines is going to be radially outward. Okay. So that's first thing that you should remember. The next one, for negative charge. Suppose we have a negative charge, how the electric lines of forces would look for a negative charge. Let's try to understand. Okay, so for negative charges also it's radially inwards. Unlike for positive it was outward, but for negative it is inwards. It is directed towards it like this. Okay, so this is how the electric lines of forces will look for the negative charge. Clear? So that's all about electric field lines and the formula for electric field. Okay, so this is what you need to understand about electric field for positive as well as negative charges. The basic idea is what is required. Okay, now what if I'm going to take two charges? Suppose we have a system of charges. Say we have positive and negative charges which are trying to interact with each other. Then how will the electric lines of forces look? Suppose I have positive and I also have a negative charge that is placed very close to each other. So how will the lines look? Okay, so the lines are always directed from positive towards the negative charge. Okay, so like this. So from positive, it's radially outward, and it is going to move towards the negative charge. Okay, so it will look like this. So this is how it looks. So from positive, it's outward, and then it moves towards negative charge. So this is a system of charges. You have to understand that the electric field lines will look like this. Now, if you see this, this looks like, the magnetic field around a bar magnet. So in smaller grades, you would have learned about the magnetic lines of forces surrounding a magnet. So this is also very similar to that. Okay, so this is a method to visualize. Okay, so that's the reason I'm showing it. I'm drawing it and showing it. Suppose if you had two positive charges. Okay, how does the electric field lines look for two positive charges? Any idea? Will it be the same way as positive and negative charge that I've shown, or is it going to be different? If it's going to be different, how is it going to be different? Any idea? If you have both charges which are positive. Okay, so when you have two positive charges, what happens? So here, because both are positive, I hope you guys know that like charges will repel each other, and so does the electric field lines surrounding them. So when you see two positive charges, you can see that the electric field lines will repel against each other. So they will not connect, they won't touch each other. So they repel each other. So it would look like this. Okay. Obviously they are directed radially outward, but how do they look? They repel each other like this. Okay. So there is no convergence. So they diverge away from each other. There is a divergence that is observed. Okay, this is how the electric field lines are distributed around two like charges. Same thing had it been negative, the arrow marks be reversed. That's it. Otherwise the diagram is one and the same. Okay, so I hope you guys are now clear with system of charges and the electric field lines around the system of charges. Okay, so this is a concept that you should know. So with that, we'll move on to the next one. So we're done with electric field lines. Okay. So we'll see what is the expression we also saw what is the expression for electric field in terms of Coulomb's force. Okay. When you substitute the Coulomb's force, this will further get simplified as E is equal to KQ upon R square. Okay. That's the formula. So these are the important, aspects about electric field. And the unit of electric field, very important, it is Newton per Coulomb. Because it is force upon charge, so it's Newton per Coulomb is the SI unit. Okay, that's the unit. Fine. So now we'll move on to the next aspect. So we're done with electric field. Okay, so force is done, quantization of charge is done, electric field is also done. So now we are going to write the expression for electric field. Okay, due to a particular point on the line of the dipole, on, you can say, axial line of the dipole. So let's try to understand this concept. So we are going to see the electric field due to axial line of an electric dipole. Okay, so what do you mean by an electric dipole? So we try to understand by a dipole. So di means two. I hope you guys know. Pole means you have two different charges which are there. So there is a polarity that is involved. Okay, so I'll show you this electric dipole. So we have a negative charge placed at a point, and we also have a positive charge. So two equal and opposite charges that are separated by a finite distance. Then you call this as a dipole. Okay, at point A, I have minus Q charge, and at point B, I have a plus Q charge. So this is what creates a dipole, and the distance between the dipole is fixed as 2a. So 2a is the length, dipole axis length. Okay, the length of the dipole axis is 2a. Okay, and now there is a dipole moment that exists from one charge towards the other. So dipole moment is basically a small force that is going to be there from one charge towards the other charge. So it is always directed from negative charge towards the positive charge. Okay, so it is from negative towards positive. So we call this as dipole moment. Okay, so that dipole moment is existing from negative towards positive charge. So it is in this particular direction, not from positive to negative. Okay, so this is the dipole moment that you will have to know. There is a simple relation between dipole moment, charge, and the distance between them. Dipole moment P bar is given by the relation P bar equals 2A into Q. That's relation. Okay, so this is the relation for dipole moment. And what is the unit for this? You can see we can write it as the length 2A times the charge. So hence the unit of dipole moment would be coulomb times meter. So combining both, you will get coulomb meter, and that's the unit of the dipole moment, electric dipole moment. Okay, so here is another concept. So this formula is again important for us. Okay, so this is I've introduced the concept of what is dipole, and we have learned how dipole moment exists between negative towards positive charge. That's the orientation. All right. So it's easy to understand dipole moment. In chemistry, I hope you guys would have learned in a molecule of HCl, you have H plus and Cl minus, right? So there is a dipole that is existing between them because two polarities are there, two different atoms with two different charges you have. So we will express this dipole moment like this. Okay, so it is always from negative charge towards the positive charge. So the same way here in physics also, we express dipole moment from negative charge minus Q towards positive charge plus Q. Okay, so you can try to correlate like that. Fine. So that's about the dipole moment. Now coming to our actual concept. So we try to understand what is the electric field at a point on the axis of the dipole. So imagine that I'm going to locate a point on the axis of the dipole. So we have a dipole, so negative charge, and then you have a positive charge. Okay, and I'm going to locate a point on the axis of this dipole. Say I'm locating a point P on the axis of this dipole, line joining the dipole. So I will call the distance from point P to the midpoint of the dipole. I repeat, the distance from point P to the midpoint of the dipole is R. So this is R. And you know that the distance between the dipole A and B is anyways going to be 2A, right? So this length is 2A. So what is our objective? Our objective is to find out what is the electric field at this point P. So the electric field at this point P is going to be contributed due to electric field at positive charge and electric field due to negative charge. Okay, because it is a system of two charges. I repeat, when you try to find out the electric field at point P, it is going to be contributed by both the charges, that is positive charge located at B and negative charge located at A. So therefore, we imagine a small test charge to be placed at point P, say just plus 1 coulomb charge. So what happens? Due to the positive charge, the electric field is going to get a repel like this. Okay, so we will express it this way. So electric field at P, due to positive charge, there is a repulsive electric field. So it will get repelled like this. So this is electric field due to positive charge. So it's towards right. Why towards right? Because like charges repel, and hence the electric field vector will point away from B. Okay, this electric field due to positive charge. But what about electric field due to negative charge? You again imagine the test charge of plus 1 coulomb placed at P. Plus 1 coulomb and minus Q, opposite charges attract. So therefore, the electric field due to negative charge will act towards left. So E minus Q will act like this. Is that clear? So like this, you try to understand the direction of the electric fields due to both the charges. And now we will write the expression for electric field due to the point P at point P. Okay, so electric field at point P. is equal to the electric field at point Q, at point, positive charge. So E plus Q, I will write it, plus the electric field due to negative charge, which is E minus Q. So we'll express it like this. Okay. So go and substitute the formula. You know that the formula for electric field is E is equal to K Q upon R squared. So we make use of this particular relation. So in terms of, for positive charge, when you go and substitute, you will get K Q upon, now R square. What is the R square? Your interest, point of interest is at point P. So the distance from point P to your positive charge will be our R in this case. So what is the distance between BP? This distance. So BP distance will be, you have to calculate it, it's R minus A. Okay, so this length BP is R minus A. So big length minus small length A will give you the remaining length. So it's KQ upon R minus A, the whole square. Okay, so this is how you express. Plus, due to negative charge, it is K times minus Q upon, from negative charge to point P, you see what is the distance? It is R plus that A. So it is R plus A, the whole squared. See, this is how you get the expression. Okay, so plus into minus, you will get a negative sign for the second term. So simplifying it further, so you can take KQ as common. So KQ, take the common out. Inside the bracket, you can write 1 upon R minus A, the whole squared, plus, it's not plus, you put minus now because overall sign is minus anyways. So minus 1 upon R plus A, the whole square. Okay, simple. Now you simplify this, children, and then you will have to write down the expression. So simplifying it, let's take the LCM and go for the simplification. So KQ, in the denominator term, you have R minus A, the whole squared, times R plus A, the whole squared, and the numerator terms for, we will write. So here on the numerator you have R squared, I am expanding and writing, plus A squared plus 2RA. Here it's negative R squared, okay, negative A squared, and plus 2RA, because minus 2RA terms become plus when you take the negative, okay, plus 2RA. Over, cancel out the terms and simplify the expression further. So plus R squared minus R squared cancel, plus A squared minus A squared also would get cancelled, and you're left with 2RA plus 2RA, which is 4RA. So you get the expression as KQ, it's KQ, inside the brackets you have 4RA upon, now can you see the denominator term is of an algebraic identity, if you can understand. It's of the form A minus B into A plus B. So I can write it as A squared minus B squared, which is R squared minus A squared. But remember, there is a whole square. So the whole squared. So we can express it like this. Alright. So now, here we go for an assumption, which is if R is much greater than A. That is, the length of point P to the midpoint of the dipole axis is much greater. If R is P is a point much away from the dipole, if that is the case, then this R squared minus A squared is approximated as R squared. Okay, if that length is too much, if it's too big, if R length is too big, then comparison to the length of the half length of the dipole axis, in that case you would write R squared minus A squared equal to R squared. To go for a simplification, okay, so we'll get this as KQ times 4RA upon R square minus A square becomes R square, the whole square is R to the power 4. So you can cancel out one R term with R power 4, so you will get this as KQ times 4, okay, A upon R cube, okay. So we'll get KQ 4A upon R cube. Now I hope you guys know the formula for dipole moment was since you know that P is equal to 2A into Q. So you try to incorporate here, substitute that here. So what happens? The expression further gets simplified as 4A can be written as 2 into 2A, right? So that 2A into Q is P. So I can write it as 2KP on RQ. And that's the answer for electric field due to axial line of dipole. This is how the expression is related for electric field due to axial line of the dipole. All right. So this formula is very important for us. Okay, we have questions based on this formula. Same way, you have electric field due to equatorial line. So I'll give you the formula for that also. But the methodology is the same. The same method you will apply. Okay, just the point P would be at a different orientation. All right, I hope this part is clear to all of you. Okay, so that's the reason I went slow and steady. So now we'll move on to the next concept, the fifth concept. So these are all concepts which we are seeing. Okay, it's a new concept. So again, we are now seeing the electric field due to equatorial line of a dipole. Okay, so equatorial line of dipole. So when I say equatorial line, again, you will take the dipole first, mark the dipole, show the dipole, negative charge, then you have a positive charge, okay, like this, and place them at 2 points. Let's call them again A and B, and midpoint of this dipole you can call it as O. All right. So now what we are doing is we are locating a point P from the center, from the perpendicular center of the dipole axis. Now this is called as equatorial point, okay, which is a straight line from the center O. So when you locate, so you will get a triangular shape. Okay, you will get a triangle like this when you complete. So that is the distances. The distance from O to P is called R. So this is R length. So OP is R, and as usual AB is going to be equal to 2A, which is dipole length, dipole axis, and dipole moment will exist from A towards B. That's the dipole moment direction. Okay, so this is the electric field due to the equatorial line of dipole. So we find out like this. So at point P, we now wish to find out what is the electric field. So same methodology you will follow this time. Okay, this time also, and you will simplify, and then you will get a final expression here as well. Okay, so that expression I will give it to you, directly. So we need the formulas. So for visualizing concept, I have shown you the illustration. Okay, so we have so many concepts like this. So we'll see the visualization part and the formulas, and then we can do all the questions. We can start solving the questions without any further ado. Okay, so I'll give you the formulas. Then we can do them. So I'll just scroll down. So now the electric field at this point P due to the dipole AB, which is located at a distance R on the equatorial line, is given by E equatorial is equal to, this time it is minus Kp upon RQ. Okay, so this is the relation, this is the formula for electric field due to equatorial line of dipole. Okay, for axial line it was 2 Kp by RQ. Here it is minus Kp upon RQ. Okay, where P is as usual dipole moment. All right. So this is the fifth concept that we have seen. Okay, going to the next one. Sixth one. Now we are going to see the torque due to dipole, which is placed in electric field. Next concept is torque due to electric dipole placed in uniform electric field. So when we say uniform electric field, so we will represent them using parallel lines. So let's draw parallel lines This represents uniform electric field. Okay. So this is uniform electric field. Now we are going to place the dipole here, at an angle. So we have a dipole. Again, I am marking it. So this is negative charge and this is positive charge. Okay, at these points. So let us name the dipole as AB. This is point A and this is point B. Okay, the length AB is 2A as usual. Okay, 2A is the length. Now what we are doing is I am going to drop a perpendicular from point B as shown. So I am dropping a perpendicular from point B like this, such that it's make an angle 90 at this point. Okay, say I will call this point as C. So you can see there is a right angle triangle ABC which is formed here. Okay, and this angle that dipole axis 2A is making with the electric field, we will call this as angle theta. So there is angle theta which is there. Clear? Now this charge Q, which is placed in the region of uniform electric field E, will experience a force. Correct? So that force is going to be directed towards right. The direction of that force will be towards right. So it will act in this particular direction. So this is F. The force experienced by positive charge, so F is equal to plus QE. It will act like this. Same way, at point A, the negative charge will experience a force, equal force, but in opposite direction like this. So F is equal to minus QE. Will act towards left. And the dipole axis in the midpoint, we will call it as O. Now what happens when there are two forces which are acting equal magnitude but in opposite direction? They will start to experience a turning effect. They will start rotating. So that turning effect of force is what is called as torque. Okay, so that is the concept of torque. So in 11th standard, all of you would have learned. Okay, in fact I have also taught. So torque is given by the letter tau. So tau is equal to, okay, force multiplied by the perpendicular distance r. Okay, so F into r, where r is the perpendicular distance. Let's go and substitute. So F is nothing but the force, right? It is given by the formula Q into E. Let's go and substitute that. Q into E into, what is the perpendicular distance? It is BC. So we should find out that what is BC equal to. How can you find the value of BC? Just apply simple trigonometry in triangle ABC. So let's apply it. So in triangle ABC, you can see that sine theta is equal to opposite by hypotenuse, which is BC, upon hypotenuse is 2A. Go for a rearrangement. So what is BC then? So BC is equal to 2A into sine theta. Clear? So we'll go and substitute that value here. So when you put that value here for BC, and what happens? You will get Q E times 2A sine theta. Okay. Now here, what is 2A into Q? I hope you guys know the formula. So 2A into Q is nothing but the dipole moment. So we will go and substitute here and get a relation as P is dipole moment, PE into sine theta. So that is how you get the formula for torque. So this is how you get the formula for torque in terms of dipole moment and the electric field. So this is the expression for torque experienced by the electric dipole placed in the region of uniform electric field. Alright. So now we can express torque in terms of vector form also. I hope you guys know that A bar cross B bar is equal to AB sine theta. Using the same logic, PE sine theta can be written as P bar cross E bar. So tau, so your torque tau bar is equal to P bar cross E bar. So in vector form, you can express the formula for torque as a cross product of dipole moment vector and the electric field vector. So there are two formulas for torque. One is the vector formula and the other one is the general expression, the general formula. Here, so this is the concept of torque. Okay, so now we have learned about torque also. We have seen what is torque. Okay, so but what is the formula? What is the SI unit for torque? If you can tell me, it will be nice. You can try. You can even give me a guess. No issues. Okay, you can try to guess. Just combine the just look at the first formula. You will understand. Force into perpendicular distance. That will give you the information about the SI unit. Always, finding out the SI unit is very important. I mean, expressing everything in terms of SI unit is very, very crucial. Okay, so what is the SI unit for this? Any idea? It is force into perpendicular distance, right? So force is in newtons and the perpendicular distance is going to be in meter. And what will be the unit? It will be Newton meter. And that's the unit of torque. Newton meter is the unit of torque. Okay, I hope this part is clear, children. So we'll move on, okay, to the next part, the next concept. So we have seen what is torque also. Okay, so now moving on. Next concept is electric flux. Okay, so we'll see what is electric flux. So electric flux is given by the formula, is given by the symbol phi E. Okay. Now, what do you mean by electric flux? What we try to understand by the terminology of electric flux. It's very simple. Electric flux is defined as the number of electric lines of forces which is passing per unit area. Okay. So if I'm taking a particular, area, say I'm taking a random area like this, I'll call this area as A, some region. So the number of electric field lines that are passing through this particular region. So we have so many electric field lines like this, say. So the total number of electric field lines that are passing through this region, you call it as the electric flux. The total number of electric lines of forces passing per unit area, normally you call that as electric flux. It's given by the formula phi E is equal to, electric flux phi E is equal to EA cos theta. That's the formula. Here you need to understand theta is angle between the angle between the electric field E and the unit normal vector of area. Okay, the unit normal vector of area, which is given as n cap. How to find out n cap? N cap is always a vector that is going to be perpendicular to a given area. So we will express like this. So what is theta then? Theta is the angle between n cap and electric field E. So this is theta. And hence we got the formula phi E is equal to EA cos theta, where E is electric field, A is nothing but the area that you are referring to, through which the electric field lines are passing, and theta is the angle between the perpendicular vector of area and the electric field. Okay, and what will be the unit for electric flux? The SI unit, combination of electric field and area. Electric field is Newton per Coulomb and area is in terms of meter squared, and hence the SI unit of electric flux is Newton meter square per Coulomb. Simple. Okay, so this is the concept of electric flux. So we have covered electric flux also. Okay, it's a scalar quantity. Okay, electric flux is scalar quantity. It's not a vector quantity because area is a scalar. Okay, fine. So we are now moving on to the next aspect, next concept, eighth concept, which is called as Gauss theorem. So we'll try to understand what is the concept of Gauss theorem. Okay. Gauss theorem is a popular theorem which tells you that the total electric flux, okay, in a closed surface. So we can say phi T, which is total electric flux in a closed surface or an enclosed surface, is equal to 1 upon epsilon naught times the charge enclosed by that surface. Okay, so according to Gauss theorem, the total electric flux inside a closed surface is equal to 1 upon epsilon naught times the charge enclosed by the surface, and the formula for this is phi is equal to q upon epsilon naught. So this is a formula for Gauss theorem. Okay, so this is one relation that you have to know. Clear? You can even combine Gauss theorem and the electric flux can be combined. So EA cos theta, it can be written as Q upon epsilon naught. That's quite possible. Okay. So moving on. So this is just a relationship. Okay. And you have to know this particular relationship. Okay. So that's for Gauss theorem. And then we have just few more concepts and we are done. Ninth concept, we have something called as the electric field due to a line of charge. So what's the electric field? Due to a line of charge. Okay, what is the electric field due to a line of charge? Now, suppose I have a long, a long wire, say like this. Okay, it's a very long wire that I'm having. Say it is from A to point B, and the charges are distributed equally, linearly on this line. Okay, on this wire. So the charges are there like this, equal distribution. Okay, and this wire of charge is having linear charge density lambda associated with it. Okay, so lambda is called the linear charge density of this wire. Okay, what is meant by linear charge density? It is charge per unit length, very similar to something called as density, which is mass per unit volume. That way we will call this as linear charge density, because it is just a wire in only one dimension. We try to express the charge, and hence you call it linear charge density. Okay, its coulomb per meter is the unit for lambda. All right, so the electric field due to this line of charge is given by the relation E is equal to lambda upon 2 pi epsilon naught r. That's the formula for electric field due to a line of charge. Okay, this is again a formula which is very useful for us to solve different type of questions. Okay, next 10th concept. Same way, now we are going to see electric field due to plane sheet of charge. Instead of now linearly, now we are going for 2 dimensions. When I say sheet, a sheet can have both length as well as breadth. Previous case, it's only a wire. Wire will only have length. Its breadth is negligible. Okay, thickness of a wire is negligible. So here, when we say plane sheet of charge, it is a sheet. Sheet will have 2 dimensions. That is, you have length as well as breadth. Okay, so it is going to be like this. There is length and breadth associated with this particular sheet, and the charges are distributed like this uniformly along the sheet as shown. Okay, so uniform charge distribution again like this. Now this time we will not call it as linear charge density. We are going to use another term which is called as surface charge density, which is charge per unit area. So here sigma is called surface charge density. Okay, that's the notation for the surface charge density. It is charge that per unit area, so coulomb per meter square is going to be the unit. There the unit is coulomb per meter. Okay, because it's charge per unit length. That's linear charge density. Yeah. So now when you write the expression for the electric field, so it is given by the relation E is equal to, for a plane sheet of charge, it is sigma upon 2 epsilon naught. That's the formula, children. Okay, so that's the formula for the electric field due to a plane sheet of charge. So we saw for a line of charge. Now we have seen for a plain sheet of torch. Okay, so this is how it is. Next, last but not the least, we are going to understand what is electric field due to a spherical shell. Okay, the last one, the last concept. So electric field due to a charged spherical shell. So what is the electric field due to a charged spherical shell? Now when I say spherical shell, it is a three-dimensional entity. So you will have a shell. Shell in the sense it is going to be a complete sphere. That is what you need to understand. It's a spherical shell of charge. So therefore in this case, so it will look like this. It's three-dimensional. So when I draw here, it will look like a circle only. You must imagine it to be a sphere. Okay, it's having a center. It's called the center as O. So we are taking three different regions. One region I am selecting as point A, which is inside the shell. Another region I am choosing on the shell, B, and another point I am choosing outside the shell. So like this, there are three different aspects where electric field can be evaluated. Okay, so O is the center of the shell, A is a point inside the shell. So if I'm going to map all those points, it will look like a circle inside. So again, point C, if you take, it will look like a big concentric circle. Okay, surrounding it like this. Yeah. So like this, there are different points. So we'll now, for each and every point, we'll understand. Okay. For any point inside, that is A. So electric field at point A. Now whenever you try to find out electric field inside a charged spherical shell, on that point there is no charge at all. Your charge is anyways on the surface. It is not inside. So electric field inside a spherical shell is always zero. And electric field on the surface, so I'm writing it as EB, that is electric field on the surface, okay, is going to be there. Electric field will definitely exist, and it's given with the relation KQ upon R square. And electric field at the outside point, that is at a point C, if I'm going to write, I will write it as again KQ upon, this time I'll put capital R square. So just to differentiate, because the distances are different. Okay, so this distance we will call it R. From O to B it is R, and from O to point C, this length, that is capital R. So clearly capital R is greater than small r. Okay, that's it. So this is the electric field at different points with respect to a charged spherical shell. From its center, so we try to understand what is electric field at various points. Is that clear, children? So now with this, we have completed all the concepts of electric fields and charges. Okay, so all the concepts are done. Now we'll see the questions. So how much we can, we'll see. So here comes the first question. Okay, so I'll give you the question. So I'll choose a Neet question itself. Yeah, here's a question. I'll just give it. First question. A charge Q is placed at the center of the line joining two equal positive charges drawing two equal positive charges, capital Q. Okay, the two equal positive charges are capital Q. The system of three charges will be in equilibrium system of three charges will be in equilibrium if Q is equal to the options are option A minus Q upon 2, option B minus Q upon 4, option C plus Q upon 4, and option D plus Q upon 2. Yes, children, you can try it now. The ball is in your court. First, try to draw the figure. You have to illustrate it as soon as possible and then solve it. Yeah, just try it out. Okay, I hope you guys have tried it. Okay, let's try to now analyze this question. So we have a charge Q that is placed at the center. Okay, somebody's given the response, I guess. Okay, minus Q by 4. Okay, good attempt. Your actually magnitude is correct. Your sign you went wrong. It's actually plus Q by 4. Okay, it's a good try. Very good. Okay, the sign is where I understand. I think you guys would have taken the sign convention. Correct? You're multiplied with that sign, isn't it? That's the reason you're getting minus Q by 4. All right. Fine. So it's actually plus Q by 4, children. So when you have, two charges, say plus Q, just draw it here. You have tried it this, exact way. That's right. But you will have you will not have negative sign. You will have a positive sign. Okay. So I'll tell you how. So here you have plus Q charge, and then you also have another plus Q charge. Okay. So let me just see. Yeah, two positive charges are there like this. Okay. This is our figure. So the figure is like this. Correct. So you have two positive charges which are there. Two equal positive charges only they are same. And you are having a charge Q that is placed here. One charge is placed here. Okay. So when you are placing it like this, so let me call this point as A, this point as B, and this point as C for simplicity. So A and C is a particular length. So that means AB and BC should be equidistant. So let me call this as, some length. So we will assume this length as X. Okay. So this is X means this is also going to be X length. So total length between A and C, we can take it as 2X. Okay. If you're going to assume as X variable midway. So having this particular, visualization, here the force experienced by charge at point A due to point B should be equal to force experienced by A due to C. I repeat, FAB should be equal to FAC. That is the understanding. Because of the charges, the system is in equilibrium. They told that all three are in equilibrium. The meaning is this. So force experienced by A due to B should be equal to force experienced by A due to C. So that is the understanding. Okay. So now we go and substitute in the formula. So when you go and substitute in the formula between A and B, so you will get K, Q1, Q2, which is capital Q times small q divided by R square, we say. Correct? So R square is nothing but going to be here X square. Okay. So we get X square like this. Same way for the other particular charge, if I'm going to write K times Q, and this time Q and capital Q again, so divided by, this time R is going to be X plus X, which is 2X the whole square. Okay, so we will get it like this. So you can see that KK is going to get cancelled anyways. Okay, you can also cancel one of the Q's. Fine, and we are left with Q upon X square is equal to Q upon 2X the whole square, which is 4X square. X square also is getting cancelled. Okay, so what is Q then? Don't you think Q is equal to capital Q upon 4? So from where did that negative sign come? It's actually positive. Okay, so the answer is charge Q is equal to capital Q upon 4. Okay, that's the answer. The answer is option C. And C is the right answer. I hope now it's clear. So this is how you will have to first denote the question, represent the question, illustrate it, then substitute it. So carefully this you will have to approach. Then you will get the answer exactly. Okay. Fine. But their net force will not be 0. Net force will not be 0. You can't say that because that is given in the question, as you have to assume that it is in equilibrium. So we will have to assume it like that. So according to equilibrium condition, you will have to consider that the force experienced by first charges with respect to the other charges has to be 0. That is the, as per the question, that is how it has to be interpreted, because many of them do a mistake here. It's not just you. Most of them do the mistake. So interpretation of data from the question is something which is very, very important, which most of them fall behind. So that is it's actually a falling in the trap. So you'll have to be very careful. The statement which tells here as the system of 3 charges will be in equilibrium. What does this line mean is that all the charges A, B and C is in equilibrium, which means force experienced by A due to B and force experienced by A due to C is equal. That's the meaning. Okay. So that's the interpretation. Fine. Sometimes it becomes a debatable topic, but that's how it needs to be interpreted. Okay, so interpretation you'll have to take care. All right. Yeah. So any doubts, children, you can ask. Okay, you can ask. So this is Neet. JE also this question has appeared, and it has also come in one of the papers. So such questions are important. So here only 3 charges. You can also have 4 or 5 in different orientations. That's quite possible. All right. So we'll now see. Now the concepts are done. Okay. So we'll see different aspects. Okay, of the questions from the next class onwards. Somebody is telling something. Why not FAB plus FBC is equal to 0? Net force in Q is not equal to 0. FAB plus BC. So when you're going to look at the force, see, I'll tell you that. You go down and then you try to understand. See here. What you're saying is fine. Force experienced by Q due to positive Q. In which direction it will be there? That will act in this direction. So F experienced by A due to B will act in this direction. Repulsive force. Where will the force due to FA and C act? That is also going to act in this direction. FAC. If you are going to talk about the charges, you see how they are acting. So they are acting towards the left. So even if you are going to take it, if you are going to assume them, so you will see that both of them are acting in a particular orientation. Okay, so negative sign convention. But when you rearrange, it is going to become positive. One of the charges, you take it the other way, it becomes positive. So I think that should answer your question. Okay, but the charges that you're seeing here, the nature of the charges play a very important role. So positive charges are only there. We don't have negative charges here. Okay, so in this case, this is the interpretation. Okay, so that we use negative. Yeah, so that is, most of the students do it like that. So they assume it like that. Both ripple means it will not attain equilibrium. Correct. It will not attain. But the question is telling that they are attaining. No. As per the question only, you will have to move. So as per logic, if we are going, things might turn out different. In the question, what they are telling, that rule applies. So you will have to blindly go with the question. Okay, correct. Both will ripple. Not yes, if you use negative charge. Absolutely agreed. That's correct. Okay. So as per the question, we are answering. Okay. Yeah. Okay, children. Fine. Yes. Then it will attain. Correct. Okay. Fine, children. So I hope you got an idea of how to approach the questions, and it's very nice that you guys are asking questions. I'm really happy. Good to have a discussion like this. But still, if you're able to unmute and ask, I will even be even more happy. Okay. So feel free to communicate, to ask questions. The more you ask, your doubts will be clarified. So that is how you can improve yourself positively. All right. So with that, I think we can wind up. Any more doubts, you can definitely ask. Before we wind up, we can see all questions. So next class, what I will do is I'll bring all the questions in the PDF beforehand, because writing questions also we are consuming time. So that way I will plan. So I'll bring all the questions so we can start solving maximum questions. Fine, we'll do it that way. All right. Yeah, anything else you can ask, children, so we can wind up. I hope the concepts are clear, the way of approaching the questions also. Okay, so we have seen just one question, but fine, we'll see many questions in the next class. All right, so we can wind up. Any doubts you can ask, children. Okay, the session is now open. Yeah, you're welcome. Okay, see, I'm not feeling bad because you're asking. You may say sometimes no also. That's fine. That's okay to ask. Okay, it's good to ask. Fine. Yeah, I accept criticism. Okay, no worries. You're all here to learn. Yes. Okay, you're welcome. Yeah. So we'll meet up in the next session, children. So until then, bye-bye. Take care. Okay. Take care of your health. Let's meet.